seconds. Okay, we can get you guys past some center. So for those of you watching at home, we just had a quick little quiz. We can real quickly go over the answers. What's the functional group in that first one? It's kind of an odd question. Stick with an alkane is really where I was looking with that. We typically don't classify alkanes as functional groups, but when they're all by themselves, that's usually a good process. Chemistry on this one. So Scottsdale people, I would expect you to know this. Chandler Gilbert, probably not. What's that? You got to do a radical. Alkanes really have no chemistry. Okay, we real briefly listed what that chemistry was on Tuesday, but we didn't really go over that reaction. I'm going to spend a little bit of time looking at that. So to run any kind of reaction with an alkane functional group, if that's all you've got, you're left to radicals. You have to do a radical reaction. Next one. So, as the general class, we could call that an alkyl halide. If we wanted to get more specific, we could call it an alkyl chloride. Chemistry. What kind of reaction class do you have available for that? We've got eliminations as a possibility. What else?
You can also do substitutions.
You can also do substitutions. Okay. The rest of those aren't very likely, so we'd probably be left with those two. Last one.
Alcohol.
We've got an alcohol. Chemistry.
You can acid base.
You've got acid base. What else? This one's a little bit harder because officially we haven't talked about it yet. Addition's not going to work. For addition, you need to have a double bond. Could you turn this into a double bond potentially? What happens if oxygen leaves? Takes electrons with it, we can generate a carbocation. There's two ways we can stabilize that carbocation. We can have a nucleophile come in, and we've got a substitution reaction, or no nucleophile, we can pull the hydrogen off, and we've got an elimination reaction. Okay? Alcohols have a lot of possible reactions that can occur depending on what you're looking at and the reagents that you're dealing with, okay, which is what we'll see today. Following starting material is that biomolecule. Anybody happen to know what that's called? It's an isoprene. Okay, an isoprene subunit. Pretty much anything biological that you can think of, any biologically made compound, has isoprenes in it. Cholesterol is made up of a sequence of isoprenes. Since you haven't heard of isoprene, I can probably say that there's 13 isoprenes in cholesterol, and no one can challenge me. I think it's 13. I'm not positive on that. Some reasonably large number. Okay. One of the things that your body will do, or any biological system will do, is react to these different subunits and either make them longer chains or start to add different functional groups or chemistries to them. Okay. So what we could go through and do is synthetically do something similar. What happens in the case of A? What do the reagents of A do? Let's do it as another option. A, B, and C all do one particular type of chemistry. What is that chemistry? Those are reagents that are reacting with alkenes. And what type of reaction? Addition. Looking at an addition reaction. What are we adding in each of these cases? adding an OH and an H. All three cases. Okay, we're adding both of those things. Let's see if I can do this with color coding. If we take a look at A, let's call A purple. Where does our OH go? Pi bond is broken in all three cases. In case of A, the OH goes there. Why would it go there? It's not so much a substitution. It happens with the first step of our reaction. The first step is that double bond comes out, reacts with H+. Okay, where does the hydrogen then go? Which carbon? Left or right? Goes to the right carbon. What happens with the other carbon? Becomes a carbocation. What type of carbocation do we have? Secondary. Is that the most stable we can get? No. Is it possible that this structure could rearrange to make a more stable carbocation? We can get a hydride shift. We can take the hydrogen with its electrons. I like to draw the little curly Q, make it stand out. And we can put the carbocation on the tertiary position. After that, now our water molecule can come in and we get our alcohol at that position. Okay? So what we have to do is evaluate each step of the reaction and be aware of these possibilities. So one of the complications with reagent A was that we can get rearrangements because we have that carbocation intermediate. So now I'm going to erase all that. Or I'll leave the OH on there. What about case B? Let's call case B red. Where does the OH go in that case? Put the OH out on the end. Okay? And what is known as the anti-Markovnikov reaction. Why does that end up happening? Because in the course of this reaction, the OH is being put into the structure through a substitution with the boron. So the hinging on this reaction is where that boron ends up going first. Boron, remember we said, had a empty p orbital. The electrons from our alkene can then go into that empty p orbital, generating our new bond. Okay? We then have to leave the other carbon with a positive charge because we took the electrons away. We're going to put the positive charge again where it's most stable on that secondary position. Okay? Once the boron's been attached, okay, and then we can have that hydrolyze or be removed in the next step of the reaction with our hydroxide and peroxide. Okay? Very last circumstance. Running out of visible colors. Let's try orange. Case C, what happens? Noticing any patterns maybe? We're going to add the OH, right? Where are we going to put the OH? Okay. We'll put it on our secondary position. I'm kind of out of space there. Our OH will get put there, which is where we would have expected it to show up in case A, but A has that problem with the rearrangements. Okay, so we get the Markovnikov addition in that case. Okay? Questions about that? Okay, so just be aware of what's happening in each of these reactions. I'm going to try and quiz you fairly frequently in the hopes that you go back and review the material every time we have a lecture. So by the time the next lecture rolls around, I will have asked the material from the previous one. You'll already be somewhat confident with it, and hopefully building up those answers faster and faster. Okay? The longest each of these quizzes will take will be 10 minutes, or sorry, 5 minutes, and I might go over the answers depending on how confident everybody is with the material. Okay? So we'll go ahead and push forward. Radical review. So this is why I said it was a bit mean. Okay, so what is a radical? We talked about a radical being an unpaired electron, okay, where the radical reactions really play a huge role when we're looking at alkanes. An alkane, as far as reactivity goes, is nothing. We don't really have anything to work with. So what we've got to do is pretty much force it to react. And we can do that in a radical reaction. So if we take a look at the substrate shown here, what we've got is propane. Okay, and I highlighted those two hydrogens, pulled them out so that we could see an extra thing that's happening. And you'll notice that as I'm saying this reaction occurs, we can put the halogen at either of those two positions. So we're going to do a radical substitution, and we're going to substitute our hydrogen for one of those halogens. If we react our halogen or our alkane with bromine, so Br2 as our halogen, the bromine goes very, very specifically for our more substituted position on the alkane. If we pick something like chlorine instead, it goes kind of evenly all over the place. It's kind of hard to predict its reactivity. It goes both to our substituted and our unsubstituted positions. What I didn't show up here is if I put fluorine on there, fluorine goes almost exclusively for the least substituted. Right? And what we're looking at with radicals is it has to do with the stability of each of those intermediates. Okay? Bromine is a relatively stable radical, at least in comparison to chlorine and the bromine, which means it can exist for long enough that we generate a stable carbon radical. Okay? The most stable carbon radical is going to be the one on the secondary position, or more substituted. Why? What makes a radical unstable? Can't look at charge. Why is a lone pair not as reactive as a radical? Electrons want to be paired. In this case, they aren't paired, which is why we have this chemistry with the radical. So how do we stabilize that single electron? We need to give it some more electrons, just like a carbocation. Okay? So if we go back to our rankings of what makes a carbocation more or less stable, we can go back and look at the electron sources around it. The more substituted our carbocation, the more stable it is. Same rules apply with our radicals. Okay? Because they want those extra electron density to help stabilize that being unpaired feature. Okay? What happens when we shift to the chloride or even the fluoride is that those radicals are much more reactive because they're smaller. Okay? So they're so much more reactive that they want to react as fast as they can, okay, so that they can stop being reactive. So what they're going to grab a hold of is the most available and easiest access positions to react at, which means our least substituted positions. Okay? So if we're going to look synthetically at why radical reactions are going to be helpful, fluoride is an incredibly bad option. Okay? Because it's not very selective. It just goes wherever the heck it feels like. As an extra thing along with it, if we attempted to do the fluoride reaction, it's actually extremely explosive. Okay? So we don't want to do it for that reason because it's dangerous. Chlorine is at least a little bit slower, okay? So we don't have to stress as much about the explosiveness of it, but we don't get the selectivity. The chlorine has more free range to go pretty much wherever it wants. So when we shift to bromine, though, we get very selective results on where our bromine does the substitution. Okay? And that's one of the reasons why when we're going to go through and deal with radicals, your only reagent is going to be bromine and then something to initiate the radical reaction. As we talked about on Tuesday, what initiates a radical reaction?
Heat.
Heat is an option. Light. Okay? The other thing that we can do when it comes to heat is we need something, a weak bond to break. That can be in the form of a peroxide. Okay? So multiple ways you can see those. Typically, if you see an oxygen bound to an oxygen, it's a big trigger for a radical reaction. So a common one is ROOR. Okay? Another one would be RO3H, RO3R. Okay? If you see those are pretty big triggers for looking at a radical reaction. So what does that mean for a radical reaction? Well, the first thing that's going to happen is we're going to generate the radical. So we could look at either of those generating the radical, but I'm going to stick with bromine in the presence of light. Light comes in, Everybody knows light is red. Ooh, that's a bad idea. The light in this case, we're using high energy light, so do we want red or purple light? Purple, because ultraviolet is higher in energy than our IR, so we're typically hitting it with some ultraviolet light, typically shown as H nu. What that causes is that bond to break homolytically. So we have to show the electrons going to each position. Okay? The result of that single step is that we generate 2 bromine radicals. Okay? This would be our initiation step, because our reaction has now started. Okay? Radicals are unstable, so they're going to try and find something to stabilize. Okay? To do that, it could just be another radical. So the bromines could immediately recombine, and now our reaction's done. Okay? We can kind of prevent that reaction from occurring by changing the concentrations of the individual species within it. Okay? So a lot of radical reactions are dependent on the concentrations of your radical initiator and the species that you want to actually react, so the alkane in this case. Okay, so if we now take a look at bringing in our alkanes, so we're not going to look at the trivial case with bromine butting up against bromine. Okay, might as well actually color these slightly different. There's one of our hydrogens, there's the other hydrogen, so red versus purple. Okay. Both of these, or these hydrogens are the only ones, or the most reactive other atom in this solution. Okay, why are they more reactive than, say, the carbons? Which is closer to the radicals? Hydrogen or carbon? Hydrogen, because it's on the outside of the molecule. Okay, we don't have to have difficult explanations. So what's going to happen is that bromine radical comes up, and it needs to pair with something, okay, anything. So what it can do is it can bring the electron in, and now that hydrogen goes, okay, I see you, let me help you out. So it's now going to take its electron away from the bond. How many electrons were in that bond?
2.
2. So we also have to specify where that other electron went. Okay, where would it likely go?
The carbon it's attached to.
The carbon it's immediately attached to. Okay. The end result of this, we'll call our red product, we get HBr. Okay, with a nice bond between them, end of our radical in that case. The bromine is no longer a radical. What happens to the carbon source?
Now it's a radical.
Now it's a radical. This is a propagation step. Propagation because we started with a radical, we ended with a radical. What happens in our other case? Okay, if we take our other bromine radical and have it react with the other hydrogen, it's still going to be a propagation, because propagation begins with P, for those of you that didn't know that. Just clarifying. We end up with HBr again, except now our radical is going to be on the secondary carbon. If we evaluate these two possible products, which one is more stable? Purple, because we have a secondary radical. So in the case of our primary, because our bromide radical is stable enough on its own, this carbon radical is so reactive that it immediately pulls the hydrogen right back off of our HBr, and we go back to our bromine radical. Okay? So we end up not seeing any of the primary radical. Why is that important to us? Well, have we finalized our reaction yet? Okay, no, we still have a carbon radical and we haven't finished our substitution. We at least got the hydrogen out of the way. Okay? If we say our red reaction has not occurred, what else do we still have left over? A bromine radical. What can that bromine radical now do?
Not reaction.
It can react with our carbon radical, again in a single electron fashion, and we can end up with our final product with the bromine at our more substituted position. Okay? Does that kind of make sense? Okay. So what we want to do is evaluate each of the mechanistic steps. Your textbook is going to go into a heck of a lot more detail than this when it comes to radicals. You see a lot more of a discussion between the bromine versus the chlorine and also fluorine showing up in it. Really what I want you to remember is synthetically, bromine is going to be your useful radical reagent. Okay. You might see questions on the ACS test that apply chlorine versus bromine. Realize chlorine is so much smaller, much more reactive. The more reactive something becomes, typically the less selective. Okay? So we want to control our reactions as best as possible, slow and controlled as opposed to fast and just a mess. Okay? So that's kind of what's going on with our radicals when it comes to alkanes. If we take a look at alkenes, alkenes can also go through a radical reaction. If we bring in bromine, okay, again, just like we did with the alkanes, we can have bromine react. It's going to react very similarly as the alkane. I don't think I've got a picture on this. No, I don't. Okay, so if we start with, it's a good thing I drew it so I had lots of space to draw starting material. We start with this alkene. When we look at the alkene, we might jump all over the reactivity of the pi bond. Okay? In the case of bromine under radical conditions, if we control the presence of bromine, we can now get the bromine to react instead of with the alkene, reacting with the alkane portion of this structure. Okay? That is known as an allylic reaction. We're reacting the bromine way out at that tail end position, and what we get for our substitution in this case is now our bromine out there. It doesn't react with the alkene. Okay? This is kind of a more difficult reaction to do because if bromine is present, we can get the addition reaction. It reacts with the alkene. So what we want to do is limit the exposure of the alkene to bromine. The best way to do that is to put in as small amount of bromine as possible so that we can get the radical initiated and we can push the radical reaction. And that's what's happening in this case. To do that, I mentioned the reagent Tuesday. The standard reagent is NBS, N-bromosuccinimide. I'm not even going to attempt, I guess I could attempt to draw it. And bromosuccinimide, there might be a double bond there. Anybody remember?
No.
You have it drawn.
I may have drawn it wrong too. It's a different slide though. So
Well, that would be yes.
it doesn't mean I drew it right. And then you've got the bromine hanging off the end. That nitrogen-bromine bond is weak. With heat or with light, you can cause that bond to break and again generate the bromine radical. The bromine radical can then push the radical mechanism. Okay, did you just look it up?
Yeah, there's no double bond.
No double bond? Okay. So we'll erase that. NBS, no double bond. Okay? So that's one way you can see NBS show up. You're looking at trying to react an alkane, but a very reactive alkane. Why is that alkane position more reactive than, say, if we got rid of the double bond? Remember, our intermediate was with the radical there. Why is this species particularly reactive? Whenever you're asked an explanation for anything in organic chemistry, the first response should be, begins with an R.
Resonance.
Resonance. Okay? Why is this radical particularly stable? Resonance. We can draw arrow pushing to shift the radical to another position. What we're doing is then stabilizing it. If we stabilize it, we can lower its energy and allow it to exist for long enough such that we can get it to react. Okay? So that's one of the different chemistries that alkenes can do as far as affecting our alkanes. Okay? Last one that we can look at. Let's just erase all that. Is if instead of adding Br2 and all that peroxide stuff, we could also go through and add HBr. If we were going to do HBr without light, okay, so let me just cross that guy out. Let's say we just did HBr with our alkene. What would you predict your product to be? Would we still expect to have the same sigma structure? Take a look at an alkene. When it reacts, what happens to the sigma structure? Sigma structure being these sigma bonds, or these single bonds through the structure. What happens to them? In the alkene? Nothing. Okay, where's the chemistry when we look at an alkene? It's typically in the pi bond. Okay? So we could draw out our sigma skeleton knowing nothing has changed. If we add HBr, H is the thing that's the most dangerous. That's our H+. Where is that going to go? Where is that going to react on our alkene? The carbon to the far right, because what's the intermediate? Carbocation on our secondary position. Okay. Now the bromide can come in, and our product of that reaction would be that. Okay. We can imply the hydrogen. Okay, so no light. Nice and happy. What happens if now we bring in light or our peroxide initiator? Any guesses what your product ends up being? I just made that up. Just seeing if you were awake. Okay. Again, we'll keep our skeletal structure, but what ends up happening is we put the bromine in an anti-Markovnikov position. It again goes back to the chemistry of how the reaction occurs, what positions are more accessible and available, and we end up putting our bromine on the opposite position. Okay. This becomes important because most reactions drive towards our standard definitions, our Zaitsev rule or our Markovnikov rule. If we want chemistry happening somewhere else, we need to come up with some other chemistry to shift and cause it to go off of non-standard appearing results. Okay? So if we want to do a substitution where we're getting a non-standard addition reaction, we can use light to initiate it and put in our bromine at that opposite position. Okay? Kind of makes sense?
So is the first one pertaining to the reaction using light?
The first one
Or is
shown
that the peroxide?
here, so up, no light, no radicals. That is a pure addition reaction, like we talked about on Tuesday. The one down below, or down, this is now purely radical. How do you know one's radical versus one's not? What are you looking for to identify that?
The intermediate.
Okay, so the intermediate would be helpful once you've established that it's going to be a radical versus not. You're absolutely right in that case, but if we haven't established that, how do we know?
What are your substrates?
There's no extra carbons. What did you say?
By
Look at
which
this.
carbon the bromine is.
That's looking at the product. What if you don't have the product? But true.
Look at your substrates.
Substrate to me means looking at this guy up here, our alkene.
You look at whether it's using light or the peroxide.
Go to your reagents. I figured that's what you're mentioning. I just want to make sure we're on the same wavelength. Okay. What's the difference between these two reactions? In our up one, what do we react? The alkene with HBr. Done. Nothing else is supplied. What happens in our second one? We react the alkene with HBr with light and a peroxide. There is information given to you in your reagents. Take advantage of that information. Look for it. If you think a radical reaction needs to occur, you have to supply that it's reacting with light or a peroxide. If you're being asked to predict the product, okay, look to see if you have light or that peroxide. Those are going to be your big signifiers and classifications that you're pushing a radical mechanism. Okay? Questions about that? Okay. Alkynes are effectively alkenes as far as your chemistry goes. There are some exceptions to this, and we'll discuss those. The most important one that's going to be relevant for you guys is when we take a look at the alkene versus the alkyne, in particular terminal alkenes and alkynes, meaning the double bond or the triple bond are at the end of a structure. We're going to see some interesting changes in our chemistry. The alkyne or our triple bond carbon, okay, due to the hybridization of the carbon, that terminal hydrogen becomes slightly acidic. Okay, why is that helpful for us? Well, if it acts as an acid, let's react it with a base. Okay, in the process of that reaction, what do I generate? Okay, and if we said it acted as an acid, we're pulling off what? H, heard it, plus, which means the carbon is negative, or an anion. Why is that neat? What kind of a species is negatively charged? Oh, sneeze. Nucleophile. How often have you seen a negative charge on a carbon? Really, really rare. Why was it difficult to put a negative charge on a carbon? It needs to take electrons from something. What measures the ability of an element to take electrons from something else? Electronegativity. Where's its electronegativity? Relatively low on the scale. So trying to get a carbon atom to take electrons from anything is very, very difficult to do. Okay? Which is why when we look at our alkanes and our alkenes, we don't evaluate that carbon-hydrogen bond. Due to the hybridization of the carbon in the triple bond, that changes the electronegativity of the carbon atom itself enough to make that hydrogen acidic. Okay? How acidic is acidic, though? It's going to be the next fun question. What base can we use to remove that hydrogen? What's a good, strong base? Sodium hydroxide. Turns out not strong enough. Okay? So when we're looking at the reagents to force this reaction to occur, we have to use an even stronger base than sodium hydroxide. The two common ones you'll see are sodium amide, or NaNH2. Why is that more basic than sodium hydroxide? Nitrogen is less electronegative than oxygen. Why would that make this more basic? If it's less electronegative, what does that mean about its ability to share its electrons? It's more willing to share its electrons. What has to happen in the case of a base? It has to share those electrons. So if we reduce the electronegativity of our element that's holding that charge, so we move from oxygen to nitrogen, we increase the basicity. Okay? So sodium amide is one of the big red flags that you're trying to react an alkyne, a terminal alkyne, to generate that nucleophile. Okay? The other common reagent that you'll see is sodium in NH3. You'll notice that is not sodium ion, that is sodium metal. Sodium metal acts as a very strong base, particularly when you dump it into NH3. Anybody know the result of that? Sodium amide in NH3. So we can either react it directly with sodium amide, okay, in which case we aren't specifying our chemistry very well, or we can show it as sodium metal being dropped into NH3. They're both referring to the exact same thing. We end up generating this very reactive amide base. Okay? So if you're trying to generate a carbon nucleophile, at this point, the only thing that you're aware of is using the alkyne. And maybe by the end of the day, we'll talk about another one. Questions about that? There are lots of other reagents or addition reagents that we could use with alkenes. There are slight variations on what can happen when you react with the alkyne. If you were going to try and convert an alkene into an alcohol, so go from the ene to the -ol ending, we have a variety of reagents we could throw in there. You could throw in our boron, our BH3 and THF, okay, followed up with hydroxide and peroxide. Puts on our alcohol. We could use mercury, okay, again, putting on the alcohol in both those cases. Turns out that when we try and do that same chemistry with the alkyne, the chemistry changes ever so slightly. Okay, so what do we mean? Let's take a look at an example here. So let's start with our alkyne. I don't particularly care what's bound to it at this point out here, so we'll just kind of leave those as R groups. If we were going to go through and do any of these alcohol reactions, okay, so one option was our BH3 THF followed by hydroxide peroxide, or our mercury with water followed by sodium BH4. All right, you got these reagents memorized now already, right? Because we talked about them last week or Tuesday. 24 hours to memorize, that's good enough. What would happen? So first off, it reacts with a pi bond. How many pi bonds can we react at any given instant? It's a hint. It's greater than 0 and less than 2. Can only react one pi bond. So let's go through and react that one pi bond. We're still going to have the other one. And since we haven't specified anything beyond stability with either of these carbons, we'll just put the alcohol on one of those positions. Right? That alcohol is located in a very interesting place, and I'm going to have to redraw it so I've got a little bit more space for this. We got our R carbon. What we've got here is an alcohol functional group and an alkene functional group. Okay, they're close enough to each other that their chemistries overlap and they start to affect each other. So we're going to learn what this functional group is called at the very end of this semester. It's known as an ene because there's an alkene, but there's also an alcohol, so it's known as an enol. Enols have very particular chemistry. They are in a tautomerization, or tautomerize, in something very similar to resonance, but it's not resonance, with the other form I guess I should have shown that other hydrogen. The other shown here. What functional group do we have now? Carbonyl. If we specify that R group is a carbon, both R groups is carbon, we have a ketone. This process on shifting between the enol and the ketone is a very famous process. It picks up its own name. It's known as the keto for ketone, keto-enol tautomerization. It's not officially resonance. Why is it not officially resonance? What happened to now our red hydrogen in the course of this reaction? Goes to the other carbon. When we do resonance, what can we do with sigma bonds? What can we do with sigma bonds in resonance? Nothing. The only bonds that we can make or break in resonance are pi bonds. This is not officially resonance because we have broken a sigma bond. It's a really easy sigma bond to break because it's a very polar hydrogen-oxygen bond, or a very polar carbon-hydrogen bond in this case. Okay? but it is not officially resonance. We're looking at what's known as a tautomerization. Okay? This reaction is in equilibrium, which is why I drew the double arrows there. Anybody know which direction it favors? Favors the ketone. We get a very small formation of the enol. Why is that relevant? If we start with the alkyne and react with either of our alcohol reagents with the pi bond, we can generate our alcohol in our enol form that immediately turns into the ketone. Do we have a carbon-carbon pi bond anymore to react a second time with these? No. It's no longer present. We're stuck at the ketone. Our reagents no longer react. Okay? So if you see any reagents that you would typically see adding to an alkene to make an alcohol, those reagents are instead going to react slightly differently with the alkyne and turn into carbonyl functional groups, okay, which might be a ketone, it might be an aldehyde, right, depending on the chemistry of the things around it, the R groups attached. If the R group on our alkyne is a hydrogen, okay, if they're both hydrogens, we'll end up with aldehydes. Okay, if one of them is a hydrogen and I react with BH3 in this first case, the carbonyl I end up with will be an aldehyde. Why? BH3 puts the alcohol where? More or less substituted. We change that R group into an H. Our alcohol, when we use BH3, goes to the least substituted. That puts our alcohol out at the tail end, which means when we go through the tautomerization, we'll end up with our carbonyl at the very end of the structure, meaning we have an aldehyde. If instead we used mercury with the exact same reagent or the exact same starting material, mercury will then go through and put the alcohol, so this was our BH3, mercury goes through and puts in our alcohol at the other position, our more substituted. Now when we go through the keto or tautomerization, we get an internal carbonyl, also known as a ketone. Okay? Kind of makes sense? I know, this is all going really, really fast because we still haven't gotten to new stuff. Last thing that I want to talk about, I'm pretty sure I want to talk about before we actually start alcohols, is looking at reducing reagents, and we're going to come back to this today as well. With alkenes, we could react them with hydrogen, and we could use platinum, palladium, or even nickel. And in the case of the alkene, we take it directly to the alkane. Okay, nice and fun. With the alkyne, however, we have two pi bonds, which means we could potentially add two equivalents of hydrogen and completely remove the pi bonds. Okay? But remember, we'd only add an equivalent at a time. So at some point, we would make the alkene. If I want to stop at the alkene, we need to be very careful with the reagents we use. If we use platinum or palladium, okay, in their pure form, we cannot stop at the alkene. Our alkyne will go all the way to the alkane. Okay, no pi bonds. If we want it to stop, if we want to isolate the alkene in our reduction reaction, we have to use what's known as a poisoned catalyst. There's a couple of them out there. Rainy nickel's a common one, and there's also a poisoned platinum catalyst that'll do a very similar reaction. And what will end up happening is you will stop at the alkene instead of going all the way to the alkane. The rainy nickel is even more interesting because it adds some stereochemical perspective to it. You end up with the cis alkene, not the trans. Okay, so it's a big, big difference when you're doing the reduction. Okay, why is that important? Why would we expect the trans versus the cis? What does a trans alkene look like? Our R groups are on opposite sides. There's our trans. Our cis, our R groups are on the same side. Why would we expect it to be more difficult to make the cis over the trans?
You get some bumping steric engines.
On the cis alkene, those two R groups are on the same side. They bump up against each other. Wow. In that process, we get some steric hindrance. They bump up against each other and make it a much higher energy alkene. So given the option, we would prefer to align our R groups as far away from each other as possible to generate a more stable or lower energy alkene. Right? The rainy nickel is particularly interesting in that respect that we end up with the cis one. Okay? Questions about those? When are we done?
55, 55.
Jeez. Is time going fast for you guys, or is it going really slow for you? Okay. We're seeing some slow, some fast. On average, it's good. Okay, chapter 13. Let's take a look at our alcohols and phenols. Okay. I don't particularly like separating them out too much as separate things because their reactivities are fairly similar, only with one big exception, and that's coming back to your acid-base characteristics. Okay? So overall, physical properties. One of the things that's going to make our alcohols largely different from any other functional group is that oxygen's very electronegative, and it's attached to two not-so-electronegative elements, which means we generate a lot of dipoles. We get a very large partial negative on our oxygen and fairly large partial positives on both the hydrogen and the carbon to which it was attached. That means with all of those possible charges, you get a lot more possible reactions. So you have to be aware of that. The other thing that this does is that then also generates really strong intermolecular forces. We jump from being a polar covalent bond with maybe just dipole-dipole forces. In the case of something like an alkyl halide, we jump to hydrogen bonding. Because we have those larger partial charges, we generate stronger intermolecular forces. That's going to then change those physical observables that we like to monitor. Particularly in the lab, we'd be looking at melting points and boiling points. Okay? So if you have an alcohol functional group, what happens to the melting point or boiling point?
They go up.
Has to go higher. The stronger the intermolecular forces, the more energy is required to put in to break them apart from each other. Okay? Remember, what we're looking at is not the bond breaking. We're looking at the forces. We're breaking the intermolecular forces that are holding these molecules to each other. Okay? This is also important when it comes to TLC. We took a look at an alcohol functional group versus any other functional group or some other functional groups. I only got 15 minutes. I'll suffer through it. Are any of our other functional groups, where would we expect our alcohol to show up on a TLC plate? Really high or relatively low?
Pretty high.
How does TLC separate?
Polarity.
Based on polarity. Which travels the furthest? Something very polar or least polar?
Least
The least polar travels the furthest. Okay, why? Because a TLC plate is made of silica, sand, silicon, and oxygen. Very, very polar. The stationary phase in TLC is so polar that the more polar things stick to it because they get a stronger interaction. The non-polar things float over the top of it. Hydrogen bonding is a very strong intermolecular force. That's going to stick pretty strongly to your TLC plate. You would not expect an alcohol-containing functional group to travel very far on a TLC plate. Okay. I don't even want to address phenols directly yet. Why are alcohols important? There are some obvious examples on why alcohols are both, I guess, fun and bad. So we'll look at some of the other options. We could look at the compound known as geranol, which your textbook supplies to you. It's isolated from roses, geraniums. I picked this compound for a couple reasons. One, we have the alcohol. What's the other big reason? Gets back to the alkenes. No, there's not any resonance there. Yep, I think someone just said it. What do we have? We have 2 isoprene units. Okay? So the natural plant put together a couple isoprene units, added an alcohol to it, and now we've got this fragrance that gets put out by these. Okay? Capsaicin and THC, a couple other things that we could put in there, both of those have alcohols. Alcohols have lots of possible reactivities, which means lots of organic molecules or lots of biological molecules carry alcohols, because it generates that very strong hydrogen bonding interaction. Okay? Nomenclature. I'm not the best on this, so we'll hit that summary slide real quickly. Remember, you've got access to this whenever you're trying to practice these. So go through and try and apply these rules, and you should get really, really close to the actual name, if not spot on. Okay? So, some examples. If we go through and take a look at the same compound here, you'll notice it's been numbered differently. So we're going to go through and name this. It's our first step. What's that? We want to find the longest carbon chain. Thankfully, that was numbered here nicely for us. So we've got the numbering set up. That gives us what name? We've got hept is where I would leave it first. Okay, now we want to come up with potentially the end of that name. What functional groups do we see in here? We've got an alkene and an alcohol. Okay, so we've got the possible endings of an al and an ene. How do we incorporate those into this?
Which one's a high priority?
We'll go back to our priority list, identify the highest priority. That is going to be the primary ending name. Which one has the higher priority? The alcohol. Okay? So our all for sure has to be the end. Our ene part of this, okay, has to also be a part of our name as well. Ene is still something that shows up at the end of a name. So instead of calling this a heptanol, where we're saying it's all singly bonded carbons, we're then going to incorporate the ene into the very end. We have heptenol. Okay? So we can specify that extra chemistry. Are there other pieces of information we need to identify here? Okay, I can start, or I can work with that. We also have the substituents. Okay, we've got one here, here, and here. What are those substituents? Methyls. So we could put in methyl for this. There's 3 of them, so we could call it, list each of those functional groups, or each of those substituents. So we've now got all of the pieces, but now the question is, how do we put all those pieces together? Okay, and that's where the numbering comes in. We need to specify where every single one of those pieces showed up. We're still identifying the same pieces. It's now just a question of, again, that numbering. Okay? As far as I'm concerned, if we named it with either numbering, would we be able to draw the exact same structure? Yeah. Why is that not allowed? Only one name is used. The other one is technically wrong. It has to do with just the complexity of naming. Okay? If everybody had 6 different names, we'd all then call each other by any one of those 6 different names. It could be very confusing very fast. So when we try and build the nomenclature rules, or when they put it together, they wanted to pick one consistent pattern. Okay? So when we go through to number this, which numbering pattern is correct, left or right? Left, because our alcohol was our highest priority. We need to specify that with our lowest number. Okay? Good thing I've got left all the spacing to be able to include all this numbering in here. Where did that show up? Where is our alcohol? It's at position 2. We have to put in the dash between numbers and letters. Where's our alkene? Position 6. So what we can do is go hept 6 ene. Whoops. Rid of that E. 2 all. What do we do about our methyls? Where are our methyls located? We've got, oh, sorry, I'm counting the wrong one. We've got one at 5, another one at 5, and another one at 6. What we can do is, again, simplify our name, and we can turn this whole system into 5, 5, 6 trimethyl heptene or hept6ene 2-ol. We've now specified where everything is. Okay? You guys all familiar with nomenclature? That was all pretty boring, hopefully.
So is the ACS, I know that depending on the year, the ACS, they switched, this is the new, do you know if ours is going to have the new nomenclature or the old? Because I know that was a problem for us in the spent sale.
Don't know about that, actually. I haven't heard anything about when we're getting the ACS tests, if we even have them. If we don't have them, we're getting new ACS tests, and I don't know how often they update it.
Because we were taught both on the assumption that depending on which year test we were getting. So.
The way I would kind of dodge that question is unless they are specifically asking for nomenclature, you're able to piece together the names, what's given to you, and draw out whatever structure is necessary without having to know the exact rules, which is why I could do well on the ACS test, because I hate nomenclature. Okay? So there's ways you can get around it. The basics that I've supplied you here in that previous slide will get you through most of the nomenclature questions. You might miss one because of that.
So I guess my follow-up question is this sapling, how they do it on sapling?
I don't know how sapling goes through and does it. I would presume they're doing it the same way because they're following the Klein textbook. The other way I can dodge that question is that you don't get a one-for-one point swap on sapling. I account for a very large error and scale your points upwards. Okay. Other questions? Are you guys confident enough with nomenclature, or at least confident enough that you can learn from the book and not from someone that hates it? Okay, good. So we'll just kind of skip those. I do want to address one extra addition here. Primary, secondary, tertiary. We still apply those same rules, but when we looked at a primary, secondary, or tertiary cation, we were looking at where the positive charge was located. When it comes to other functional groups, sometimes that primary, secondary, tertiary nomenclature becomes a bit odd. The alcohol isn't too bad. So what we'll do is look at the carbon where our alcohol is attached and evaluate what things are attached to it. If it is attached to one other carbon, we have primary. 2 other carbons, secondary, 3 other, 4 other. Not possible because can't also have an alcohol and 4 carbons attached. That would be too many bonds. Just test it. Okay? I thought I was going to hit this slide earlier. So now what we're going to do is kind of push into the reactivity of our alcohols. Okay? So you've seen this slide already as it applied to the other functional groups, and we kind of walked our way through our alcohols. Wanted to zoom in a little bit on the structure so that you could see that chemistry a little bit better. Okay, so when I ask you for what chemistry is possible for an individual structure, what you should be doing is looking for very large pieces. Okay, those pieces being elements that are high in electronegativity. Why look for elements that are high in electronegativity? They like to do chemistry because they like the electrons, or particularly the bonding electrons near them so much that what happens?
Partial negatives, partial positives.
We generate a very large partial negative on that oxygen because it starts to steal the electrons from the carbon and the hydrogen. Okay? That gives us, oh man, I should color code better. Except it goes back to this. If we then look at our blue, we generate that very large partial negative. Electron density pushes towards our oxygen. So our oxygen can then act as a nucleophile or a base because it has that electron source. The other thing that it does is that necessarily means the carbon and the hydrogen become very large partial positives, which then opens up their chemistry, which is largely what the chapter 12 is looking at. They're trying to get you to look at each functional group and identify the possible chemistries with it so that you can try and propagate forwards or backwards. Okay? So once we've identified these partial charges, that can help us decide where we can go from there or where we can then work backwards from. So if I wanted to make an alcohol, okay, what things do I need? What bonds make this an alcohol? How about this one out here? No. Okay. We have the carbon hydrogen. Sorry. Let me try that again. We have the carbon oxygen bond. So we could get real simple on this. How do I make an alcohol? Well, let's start with a species that didn't have that hydrogen. Ta-da! How do I make an alcohol? Add a hydrogen. I add acid. There we go. There's a synthesis of an alcohol. Okay? What's another option? What other bond makes up an alcohol?
Carbon oxygen.
We also need this carbon-oxygen bond. Okay? So I could then work backwards and say, okay, I don't start with that. Let's put in a positive carbon. And now I need to add something where that oxygen comes in with the OH. Oh, there we go. Ta-da! There's my alcohol. I reacted these two things. Okay? So the idea is finding those polar bonds and then breaking them and seeing what you can do to generate them. Why is this one not a particularly good option for synthesizing an alcohol? If you go out to the store, will you be able to buy something that supplies hydroxide, OH minus? A chemical store. Yeah. Why do you say yeah? Where can you get hydroxide from? Sodium hydroxide. Awesome. We can buy that any place. That's reasonable. Where do you buy this guy? Nowhere. Why not? We can't stabilize it very well. So we would need to change that positive charge somehow because we can't get that purchased easily. We need to stabilize it with something that could possibly be removed easily. What something could possibly be removed easily, leaving a positive charge?
Halide?
Let's toss in a halogen. What type of reaction am I trying to do to now make my alcohol? Substitution. Okay? So identifying what bonds need to break or make in either direction, we can start to predict something about what these groups can do, where they came from, and how we can make them. In a lot of cases, you're just making something up. Why did I pick bromine and not chlorine or iodine? I like bromine. That's about it. Okay? So the idea is to identify something as quickly and easily as you can and start filling in those pieces. Okay? That's the idea behind retrosynthesis, and that's one of the things you're going to be trying to do in this class and with multiple synthesis steps. Identify that chemistry and start to put pieces in that you know you want to show up. Okay? So, one of the things I think I'll zoom through here, just because I'm hoping you guys are more confident with your acids and bases, we could look at the acid-base characteristics of an alcohol functional group. In the first reaction, what is the alcohol acting as? It's acting as an acid because, how do you identify it? What changed? If we compare our alcohol, this piece, to its conjugate partner on the other side, the thing that changed was that hydrogen. Where'd that hydrogen go? To our negative oxygen. So what we're doing is trying to identify again what changed in the course of this reaction, what thing best fits that. Okay? In this course, or in this step, what we did was a standard acid-base reaction. Okay? We switched the location of that hydrogen atom, and that was all we changed. What happened in the bottom case? What did the alcohol act as?
Base.
A base. How do you know that?
It accepts the hydrogen.
It accepts the hydrogen. We've formed that new bond. Okay? So it's again identifying those pieces. How confident are you guys in identifying pieces? Solid? Okay. You just set yourself up for fun. Okay, so Tuesday we'll write a new quiz. I'll give you a new reaction. You get to identify all the pieces that were made and broken in there. We'll make it challenging. Okay. Wednesday. What is today? Wednesday. So yeah, Wednesday. Oh, and you got a whole week to prepare for it. Even better. Okay? So what we want to do is, again, identify these differences and try and come up with ways to push these reactions. Okay? In the case of either of these, would we expect these to be very favorable reactions? Okay? In terms of determining favorability, what we can do is look for the most reactive thing. What's the most reactive thing in the top reaction on the reactant side? Take a solution, I throw it at you. Which one are you concerned about? The alcohol or hydroxide? Hydroxide, why? It's charged. Take a look at the products. What's the most reactive thing? Our conjugate base. Why? Negatively charged. What's the difference in stability between the negative charge across that reaction? Okay, why? So what we're hoping is that we could then evaluate and see some difference between it. Turns out there's not a lot of difference between this. That oxygen tends to shield a lot of the other interactions around it. And we don't see a big difference between either a carbon and a hydrogen, or sorry, an oxygen and a carbon versus an oxygen and a hydrogen. Okay? That subtle difference means that these reactions are typically in equilibrium. They go both forwards and backwards. Okay, so if we want our alcohol to act as a base, we need to add a stronger base. If we want it to act as an acid, we have to add, sorry, a stronger base. I did those backwards. If we want our alcohol to act as an acid, we need to add a stronger base than hydroxide, okay, to make sure that we push towards the products. If we want our alcohol to act as a base, we need to make sure that we add a stronger acid so that, again, we can force that reaction. So we stop sitting in equilibrium. Equilibrium is boring. Okay? So we can use things like hydroxide, not the best. Other big options, we could use sodium metal. Okay? It's a good strong base. We can use sodium hydride. Okay, as well. Both of those would be good strong bases. As far as the strong acids, okay, we could add our, by definition, strong acids, sulfuric acid, HCl, HBr. Okay? And that's where we'll pick up next week, largely with our complications with those strong acids. Okay? Thank you for your patience.